Before we talk about the transformations of the graphs of sine and cosines, let's review what it means to be the transformation of a graph in general. I'm going to start by graphing y equals x squared. This is a pretty familiar graph to most of us. In fact, most of you have just finished a course in Pre-Calculus 1, which is primarily algebra, which is where we learn how to graph what we call the toolkit functions, the linear function, the quadratic, the cubic, the reciprocal function, and so on. But in addition to just the toolkit function, we also learned how to graph things that look like that function, but are different in some way. For example, we know that the graph of y equals x plus 2, quantity squared, looks just like the graph of x squared, but it's moved over 2 units to the left. I didn't do a very good job with my curve there. That's not too bad. The graph of y equals x squared plus 2 also looks just like the graph of y equals x squared, but it's shifted up 2 units. The graph of y equals 2x looks just like the graph of y equals x, but all the y values are doubled. So instead of going through the point 1, 1, it goes through the point 1, 2. This has the effect of stretching this graph vertically. It makes it skinny, tall and skinny. I think I want to put this one over here, actually. And then we also know the graph of y equals negative x squared is the same as the graph of y equals x squared, but it's upside down. And this one's a hard one to see, but y equals negative x inside the parentheses squared looks like just like the graph of y equals x squared, but instead of having its right side on the first quadrant and its other side in the second quadrant, its one side will be in the first quadrant and its opposite side will be in the second quadrant. In other words, it gets flipped around the y-axis. In this case, that graph ends up looking just the same as the original. That's not always the case. For example, y equals x cubed looks like this. But y equals negative x cubed looks like this, because it's been flipped around the y-axis. Now, all of these can be combined so that I can end up, for example, graphing something like y equals 3 times negative x plus 2 quantity squared minus 1, just by using transformations. The graph of this function here would look just like the graph of y equals x squared, except that it would have been shifted to the left 2 units, flipped over the x-axis, stretched by a factor of 3, so made really long and skinny, and then the whole thing moved down 1 unit. It would look something like this. Let's see, I need to go to the left 2 units and down 1 for my vertex. And then I'm going to be upside down, but instead of going through the point 1, 1, I'm going to go through the point 1, 3. This graph looks something like this. Well, this is exactly what we're going to do with sine and cosine. I can take the graph of y equals the sine of x, and I can shift it to the left or right. I can shift it up or down. I can flip it over the x-axis or the y-axis, and I can combine. I can also stretch it. So with this review out of the way, let's go ahead and take a look at y equals the sine of x and all the things you can do with that. I'll start by saying something I almost dismissed the last time, and that is that instead of using the variable theta here, I'm using the variable x. The main reason for that is that I'm thinking of this thing right here as a function, rather than simply just the value of sine at one particular angle. So for the rest of this section, I'll probably just use x instead of theta, but it's worth being able to sort of think back and forth between the two. Sometimes you'll see y equals the cosine of theta. Sometimes you'll see y equals the cosine of some other Greek letter. y equals the cosine of x, y equals the cosine of t, and so on. Our graph, y equals the sine of x, looks something like this. We know it only goes up to 1 and down to -1. And we know that it goes out to 2 pi before it starts to repeat. It gets to its maximum value and its minimum value halfway between 0 and pi and halfway between pi and 2 pi. So let me plot some critical points here, and then we'll go back and fill it in. So this is kind of a shortcut way to graph the sine now that you know what it looks like. 0, 0, pi 0, and 2 pi 0, pi over 2, 1, 3 pi over 2, -1. And then being careful not to get too angular, you can just fill in the blanks. A nice curve, a nice smooth curve that goes between these 2 points. Well, there's more than 2 points here. I guess what I meant was between these 2 points, the beginning and the end, but of course it goes through all these other points as well. This isn't perfect, but it gives us an idea of what the sine function looks like. Keep in mind that this can go on in both directions forever. I'm not going to bother with more than one period of sine because once we know what it looks like, we know that it looks just like that for every other period, the one beyond pi over 2, the one beyond that, and the one before 0, and the one beyond that, and so on. So to demonstrate what I want to talk about today, I'm actually going to go back over this in a white pen, and then I'm going to use different colored pens to show each transformation. Let's start by talking about all the different transformations we can do with the sine of x. We can have y equals the sine of x plus a constant. We can have y equals the sine of x plus a constant. Now, I don't know if you remember this from algebra, but this one, imagine that this is x squared. This one here says take the graph of x squared and then raise the whole thing by a constant value. This one says take the graph of x squared, move it to the left by that constant value. Another thing we can do is stretch them. So I could say a constant times the sine of x. There's a very special constant we should talk about separately, and that is -1. What does the graph of negative the sine of x look like? Now, for the sake of demonstration, I need to know what c is if I'm going to graph this function. What I'm going to do here is just erase the c and replace it with a constant. I don't need to worry about the last one because its constant is -1. So I'm just going to use 2 in each case here, and I'll start by graphing the first one, and I'm going to do it in yellow. So I'm going to highlight the function in yellow, and then I'll do the graph of the function in yellow as well. The thing to keep in mind is y equals the sine of x. Imagine covering this up. Y equals the sine of x is already here. And so to graph y equals the sine of x plus 2, all I need to do is take each of these points and put them higher by 2, every single one. So I'm going to start by extending my y-axis a little bit so I can get up to 2. And then I can plot 0, not 0, 0, but 0, 2. That's 2 units higher than that sort of first important point that I plotted there. One that's 2 units higher than this one is going to have to go all the way up to 3. So it looks like I'm going to have to extend my graph again. Up to 3. And then I can plot the point not pi, that looks like pi over 2, 1, but pi over 2, 3, because that's 3 units high, or 2 units higher. At pi, I'm going to go up to 2. At 3 pi over 2, I'm at -1. If I add 2 to that, I only get up to +1. And then I have to add 2 to the y value of 0 at 2 pi as well. And then I can just connect the dots in the same way as I did with the graph of y equals the sine of x. So this graph here in yellow goes with the highlighted function in yellow. You can see that it just looks just like the sine of x, but it's 2 units higher. Okay, I'm going to skip the next one for now and come back to it. I want to talk about this one next. I'm highlighting in blue y equals 2 times the sine of x. Well, if I know what the graph of the sine of x looks like, then 2 times that tells me that all my y values are doubled. So I'm going to take my white graph and double all of these important values. I'll graph that in blue. And that'll give me the graph of 2 times the sine of x. Well, 2 times the sine of x, when x is 0, the sine of x is 0. 2 times the sine of x is 2 times 0, which is still 0. So actually, wherever I have a 0, I'm going to retain a 0. That's not going to change. Here my x value, or my theta value, is 0. Here it's pi, and here it's 2 pi. In the previous video, we looked at the fact that all of the output values for these three, for 0, pi, and 2 pi, for sine, the output values were all 0. So the sine of x, let me put it in parentheses, maybe that will help a little bit. The sine of x is 0 whenever x is 0, pi, or 2 pi. Now, when x is pi over 2, the sine of x is 1, but I need to double that. So I'm going to go up to 2. And when x is 3 pi over 2, the sine of x is negative 1. When I double that, I get negative 2. Connecting those dots, I get something that looks like this. And just like graphing y equals x squared and y equals 2x squared, you see that the result is a graph that has been stretched. Its y values have been doubled. That's what this thing is doing. All right, now I'm going to graph y equals negative the sine of x. Don't worry, I'll come back to that sine of x plus 2 in a minute. Y equals the negative sine of x. I'll do that one in green. Well, just like the graph of y equals x squared, if you put a negative in front of it, it flips it over the x-axis. So all I need to do is take each of my y values and negate them or change their sign. The opposite of 0 is 0, so the y value of 0 doesn't change. Everywhere I had a 0, I'm going to still have a 0. But where I had a positive 1, now I'm going to have a negative 1. And where I had a negative 1, I'll now have a positive 1. And so this graph ends up looking something like this. Okay, our last one is y equals the sine of x plus 2. I'll do that one in pink. Remember graphing y equals x plus 2 all squared? We took the graph of x squared and we moved it 2 units to the left. And that's exactly what we're going to do here. What makes it tricky is that I don't know where 2 is because my axis has been very carefully labeled in terms of pi. So if I carry on thinking about my axis as being labeled in terms of pi, then this is negative pi, which is about negative 3.14. So that's a little too far, but pi over 2, negative pi over 2, is only about 1.5, negative 1.5, 1.6. So that's not quite far enough. So in each case, as I take these important points and move them to the left 2 units, I'm not moving them 2 tick marks. I'm trying to move them 2 units, 2 numbers, 2 integers. That's about 1.6. That's about 3.14. Somewhere in between is negative 2. Negative 2, or 2 units to the left of where this point was, this original first point on the white graph. The next point on the white graph is this one here, and I'm going to do the same thing. Notice how when I moved this, when I ended up moving it about 1.5, just a little over 1.5 units. So I'm going to do the same thing now for each of these. There's 1 unit, there's 1.5. Down here I'll go 1 unit, 1.5. All right, so my top value here, this is pi over 2 comma 1. I'm going to move that 2 units to the left so that it's about there. And then I have another pi comma 0. I'm going to move that 2 units to the left. Not 2 tick marks, 2 integers. Negative 1 have pi, 3 pi over, what is that? 2 pi over 4 pi over 5 pi over 4. I'll move that 2 units to the left. That's going to go about there. And lastly, 2 pi 0 becomes 2 pi minus 2, comma, 0. And then I can connect the dots. I'll start that again. So this pink graph here goes with that pink highlighted function. So now you can see that I've done each one of these transformations, a vertical shift, a horizontal shift, a vertical stretch, and I don't know what to call that, a flip, right? I flipped it over the x-axis. Actually, I would like to do one more. It just occurred to me that I've kind of missed one here, and that is y equals the sine of negative x. So this one I'm going to do, well, I only have so many colors in this software. I've used yellow. I've used all my colors, so I'll just do it in white. So I'll do this as a white box. Keep in mind that my original white function here is y equals the sine of x. That's this big fat white line right here. I'm going to graph y equals the sine of negative x, also in white, but it'll be a thinner line. Okay, so now remember what happened when we did y equals negative x cubed. Here's y equals x cubed, sort of. Here's y equals negative x cubed. And that's not because it flipped around the x-axis, although the same thing happens, and that's because it's an odd function, believe it or not. We flipped it around the y-axis. So in order to graph y equals the sine of negative x, I need to take each one of these points and move it to the other side. So one way to think about this is to graph 0, 0 where it lands, because it is, even when you flip it, nothing changes. Graph this point over here, pi over 2, negative pi over 2, comma 1. Graph this point over here. Can you see how I'm thinking about each one as being moved across to the other side? I need some more room on my axis though. All right, so far I've moved this one without really moving it. This one came over here. This one came over here. Now this one needs to come over here. So that puts it down here. And the last one is negative 2 pi 0. And I have something that looks like this. Now that is a perfectly legitimate way to graph y equals the sine of negative x. But it's kind of hard to tell what's going on, partly because I'm limited in the colors that I can use here. I'm actually going to change this to yellow because it's a little bit less in conflict with the other yellow graph that's up there. So watch as I change this to yellow. So just the part that I just now graphed, which is y equals the sine of negative x, is right there. Now all these other graphs are kind of from 0 up, right? We started at 0, x equals 0, and we moved to the right to graph our other points. This one we kind of went backwards, and that's okay, but one thing we might want to try doing is getting that graph into the same sort of range of values for x as the other graphs are using. It's more common to see a single period of a function graphed from 0 to the right. This is not wrong. This is fine. It's a single period of y equals the sine of negative x. But if I want it to be over here with the others, then all I need to do is think about it as continuing from where it's currently sitting here. If I were to continue graphing this cycle, I'd be coming down first, and then up, and then back down. I'm going to do that in yellow. From here, back to 0, and then down, right? So this part of this function here, the second half of this yellow function here is a single period of y equals the sine of negative x. It happens that I've covered up my green graph, And so y equals negative the sine of x and y equals the sine of negative x are the same. It's somewhat unfortunate that I've ended up covering up I keep grabbing the wrong pen. I've ended up covering up my graph of the sine, negative the sine of x. So I'm going to kind of try to put that back in as a dotted line so you can see them both. Now, these two things here, let me see. Yeah, these two right here. The fact that they're equal is quite interesting. I can say y equals negative the sine of x, or I can say y equals the sine of negative x. And this is actually what we mean by an odd function. This is the definition of an odd function. If I rewrite y as f of x, then I get the opposite of f of x on this side, the opposite of sine, just the normal sine of x, but the negative of it, the normal f of x, but the negative of it. On this side, I get the sine of negative x. So if I take f of x and plug not x into it, but negative x into it, if these two things are the same, we say the function is an odd function. That's the definition of an odd function. Okay, so now we've seen what the various different transformations look like on a sine function. I've used 2 in each of these cases, but I could have used a 1 or I could have used a -3, right? I could have done that with any of these. Let's take a look now just at a couple of them on the cosine graph. We'll start with a reminder of what the cosine graph looks like. It starts at 0, 1, and it ends at 2 pi, 1. Halfway in between, it's at its other extreme, pi, -1. Between each of these pairs of points, it's at 0. So I'll have points there and there. Now again, I have to be careful not to make a V out of this, but a curve. So there is one cycle or one period of the graph of the cosine of x. In this case, I'm going to start with our special cases of y equals negative the cosine of x and y equals the cosine of negative x. The cosine of negative x, negative the cosine of x is just the graph of the cosine of x, this graph right here, flipped over the x-axis. So if I take each one of my points and make it negative, or negate it, or change its sign, I'll get this graph here. On the other hand, if I graph, let's see, what color should I use for this one? Maybe pink. If I graph y equals cosine of negative x, now this time I'm flipping it not over the x-axis, but across the y-axis. So this time I'm going to take each one of these points and think about moving it to the other side. So from pi over 2, I'm going to go to negative pi over 2. From pi, I'm going to go to negative pi. At 2 pi, I'll go all the way over to negative 2 pi. And I'll do that. This one doesn't change. Let's see. At pi over 2, I was at 0. So now I'm at negative pi over 2, 0. At pi, I was at negative 1. So now I'll be at negative pi, negative 1. 3 pi over 2, 0. Negative 3 pi over 2, 0. And pi over 2, positive 1 becomes negative pi over 2, positive 1. And so again, being careful to make sure that my graph is curved, I get something that looks like that. And I didn't do a very good job on that last bit. Let me try this part again. That's a little better. Now again, I'm sort of over here in the negative world, right? So if I take this graph starting here, going down through 0 to negative 1 to 0 to 1, and I continue it, then I'm going to get a repetition of this graph over here. So I could, because this is actually one cycle here, one period, if I just continue, I'll get a second period of the same graph. And from that, you can see that the cosine of x and the cosine of negative x are the same. So this time I can write that the cosine of x and the cosine of negative x are the same. The difference between this one and the sine was in the case of the sine, we had another negative out here. This is not the same function, and it doesn't behave in exactly the same way. But we do have the cosine of x is equal to the cosine of positive x is equal to the cosine of negative x. So I can write the cosine of x as a function f of x, and the cosine of negative x as a function f of x, where I replace x with negative x. And those two things are equal. And that is the definition of an even function. I told you you'd be seeing those again. Now I can check this by plugging in some values. I'm not going to spend much time doing this, but let's say I want to check whether this is even or odd. I'm going to take the cosine of some negative number like negative pi over 4. I'm going to use my chart to find that the cosine of positive pi over 4 is the square root of 2 over 2. And if I plug in a negative pi over 4, that's a negative theta value, right? So that's like going backwards around the circle. And when I go backwards from 0 by pi over 4, or 45 degrees, I end up in quadrant 4. Well, in quadrant 4, cosines are positive. Let's see, I want to erase this question mark here. It's kind of in my way. So now I'm going to check and see what the cosine of positive pi over 4 is. And I can do that just by looking it up on the table. And that's the square root of 2 over 2, and that's positive. So it's true that the cosine of x is equal to the cosine of negative x, which makes this an even function. Now, I've only checked this for one value, so it's not considered a proof, but it might help you verify. This is what we mean by an even function. In the same way that, let me write it out again, negative the sine of x was equal to the sine of negative x, and that's an odd function. Now, I've only looked at a couple of very special cases so far for cosine, but I want to point out that you can do the same thing with cosine as you can with sine. In other words, I can take this white graph and shift it up, shift it to the right or left, stretch it or shrink it, or as we've seen here, flip it over either the x-axis or the y-axis. There's one more example I want to do, and that's y equals the cosine of x plus or minus something. And in this case, I'm going to use x minus pi over 2. So we're going to shift the graph of cosine, that's this graph right here, to the right by the amount pi over 2. I'm going to do that by starting with a new graph down here. First of all, I'm going to graph my cosine function. So if I go up to 1 and down to negative 1, the cosine function looks like this. It's highest at the beginning and end of its period, it's lowest halfway between, and then it's 0 halfway between each of those pairs of points. Now I'm going to graph by connecting the dots, making sure my graph stays curved. And now I'm going to graph y equals the cosine of x minus pi over 2. I'll do that in blue. So I'll be using a blue pen. Now remember that what this means is take your original graph, y equals the cosine of x, and shift all the important points over by pi over 2. So I'm going to take this point and move it over pi over 2, and this one by pi over 2, and this one, and so on. Once I've done that, I'll connect the dots. The first one is 0, 1, so now it needs to be pi over 2, 1. This point is getting moved over pi over 2 units. Let's go ahead and plot that. And then looking at the next point, it's currently at pi over 2, 0. So I need to move it to the right so that it's at pi over 2 plus pi over 2, 0. That's pi over 0. Pi, 0, sorry. Then this one down here is at pi negative 1. So I'm going to move it to pi over 2 units to the right so that it's at 3 pi over 2, negative 1. And then I'll move this one over and I'll move this one over, and I'll connect the dots. So you can see that we can also affect horizontal changes with cosine. In fact, you can do this with any function. Now, the reason I chose this one to do as my last example is this. I'm going to make a slight change to my pen, just make it a little thinner. And then let's make the observation that since I can go on indefinitely, and I can do that in either direction, I could continue this graph so that it looks like that. And then instead of waiting to get all the way over to 2 pi plus pi over 2 to cut it off, what if I cut it off back here? Well, that looks an awful lot like the graph of y equals the sine of x. And that's exactly what it is. It has all the same important points on it. They're just shifted over. So we can actually write that the sine of x is equal to the cosine of x minus pi over 2. Those graphs are actually the same, which means that the sine is just a shift of the cosine graph. They have the same shape. Remember, this one actually came up here. And in fact, I can take my cosine graph and continue it as well if I want to, and then cut that one off. I don't really need to cut them off, but it makes it easier to see. That's now just a sine graph. So I'm actually going to put my graphs back in place because I don't want to lose sight of the fact that we are working with more than just that small piece of the graph or that truncated piece of the graph. But this part here is done in a thinner pen to indicate it wasn't part of the original graph, but that this graph, starting at 0 and ending at y equals 0, is the same as the sine function. So the sine function is just a horizontal shift of the cosine function. It's not just any horizontal shift, though. If I took, get the right pen, if I took the cosine graph, in fact, let me do this. Y equals the cosine of x plus pi over 2. I'll do this one in yellow. So I'll highlight this in yellow. Grab a yellow pen. Now I'm going to move to graph this. I'm going to take the cosine of x and move everything to the left pi over 2 units. So I'm going to go this way. I'll have this one over here, this one here, this one down here goes here, that one goes there, and that one goes there. I have something that looks like, I'm not doing a very good job. There you go. So you can see that that is still a cosine graph. Oh, that's a really bad piece right there. Let me see if I can fix that. That's better. All right, so now my point here was that if I take this graph and continue it, I'm not making a sine graph. The only piece that I can see, I think I'll use a highlighter, the only piece that I can see that looks familiar is this piece right here, and that is a negative sine graph. It's a sine graph. The yellow graph is a sine graph that's been flipped over the x-axis. So it does matter whether you have a minus or a plus in your parentheses here. These graphs are both legitimate. This one gets shifted to the right pi over 2 units. This one gets shifted to the left. What's important here, the distinction we need to make is it's that only the one with a minus in it that's equal to the sine graph. The other one happens to be equal to the negative sine graph, but that's not saying the same thing. Okay, there is one more thing I want to do here. I want to do a stretched cosine graph. And the main reason for this is so that we can talk about one new piece of vocabulary. We already know about the period of a graph. It's how long it takes to get from, let's see, I'm doing cosine, so I want 0, 1, 2 pi 1, negative pi, negative 1. My scale's a little bit different this time. That's on purpose. And then I'm going to try to connect the dots as smoothly as I can. Kind of missed a little bit there. Okay. Now, what 3 cosine pi looks like. Let's see, what color should I use? I've used all my colors again, so I'm going to have to pick something. I'll go with pink. 3 cosine of x just triples all of my y values. So where I have a 1, I'm going to have a 3. Where I have a 0, I'm still going to have a 0. And where I had a negative 1, I'm going to have a negative 3. And this stretches my cosine graph by a factor of 3. We call this stretching, in terms of the graph, amplitude. When I talk about the amplitude of this particular graph, I'm going to say it's 3, because that's how much the regular cosine graph has been stretched. 3, and it's right there in front of the function. You can see it right there. Just like I can say this horizontal shift is pi over 2 to the right, I can say the amplitude of this graph is 3. Okay, now all we need to do is summarize. We've just been talking about the sine and cosine graphs, or the sine and cosine functions. And the reason we talk about these together is, well, there are actually several reasons for it. One is that the sine graph is just a transformation. In fact, it's a horizontal transformation of the cosine graph. So they're very closely related. Another is that they both have a period of 2 pi. And for this reason, we can lump these two together as being similar enough that they kind of deserve their own little summary. So we can say that y equals a times the sine of kx, and y equals a times the cosine of kx. K here is just a real number. K is a member of, or an element of, the set of real numbers. That's all that means. So K is some real number. And for both of these, we have an amplitude of A. So whatever the number is in front of the function, A here and A here, and again, A is just a real number. It doesn't have to be an integer. It often is in a textbook setting, but it isn't always. So A is a real number, and A is the amplitude of the graph. Remember when we graphed y equals 3 times the cosine of x? The graph looked just like the graph of the cosine of x, but we stretched it by a factor of 3. So its amplitude was 3. We have an amplitude of whatever number is in front here. That's an easy one. The harder one is that they both have a period not of 2 pi, but of 2 pi over k. And here's why. Let's try graphing y equals the sine of 2x. Well, I know that the sine of 0 is 0, and since if I plug a 0 in for x, I still get 0 here. The sine of 2 times 0 is still going to be 0. Then I also know that the sine of pi is also 0, but to get pi in here, I'm going to have to enter pi over 2 for my x, because 2 times pi over 2, the 2's will cancel, leaving me with pi. So for the entry value, for the input value of pi over 2, I get 0. I also know that the sine of 2 pi is 0. But to get 2 pi in here, my input is going to have to be pi. So when I input pi, I get 0. Now what I'm used to doing is having a 0 here, a 0 here, and a 0 here, and then filling in the high and the low. But since my input values, to get values in the parentheses of 0, pi, and 2 pi, I had to input 0, pi over 2, and pi. My maximum and minimum values are going to be halfway in between those, halfway in between 0 and pi over 2, and between pi over 2 and pi. So the graph ends up looking like this, which doesn't look that different from the sine of y equals the sine of x. but y equals the sine of x looks like this. So what having a 2 inside the parentheses does, just as it did in algebra, this was the hard one for most people, it certainly was for me when I was learning algebra, was instead of doubling the amount of time it takes to get from 0 back to 0, it halves it, right? So I think the easy way to think about this is by extending this graph, putting a second period of this graph in. I'll just go ahead and do that here. So there are 2 copies of my y equals the sine of 2x. By way of a reminder, the wrong color, y equals the sine of x has a period of 2 pi. Y equals the sine of 2x has a period of only pi. That's how long it takes me to get from my starting point through one cycle to a place where I'm ready to start again. It only takes pi. Period here is pi. And so how do you remember this? Well, the way I remember it is this. If it takes sine 2 pi to get from start to finish, that's my skinny white graph here. If it takes it takes sine 2 pi to make that one cycle, it's going to make this many cycles. This graph is going to make this many cycles in that same amount of space. So between 0 and 2 pi, I'm going to go around twice. If this was a 3, I'd have 3 periods, 3 cycles of sine. If this was a 5, I'd have 5 cycles of pi, and so on. So this has how many cycles there are between 0 and 2 pi. Between 0 and 2 pi sort of being the magic number, the thing that you're going to remember about sine is that it has a period of 2 pi. So the sine of 1x goes from 0 to 2 pi in one cycle. The sine of 2x goes from 0 to 2 pi in 2 cycles, right? So how do you figure out what the period is? Well, it's pi, but it's not always that easy to look at and just pick out. So we need kind of a formula. And here's that formula. The period, you might call it P, is equal to the normal period of pi, which is 2 pi, divided by however many cycles there are in that amount of space, divided by k. Okay? So, for example, if I have y equals the cosine of 7x, its period is going to be the normal period for pi divided up into this many cycles, right? I'm going to get 7 cycles of cosine between 0 and 2 pi. So take the normal period and divide it up by that many cycles. That's the period of the cosine of 7x. That's why the period of sine of 2x is pi, because its period is 2 pi divided by how many cycles we actually get. That's 2 in this case, and that gives me a period of pi. Okay, let's see if we can tie this all together. There's one more thing I'm going to talk about, and that is what happens when you combine all of these together. All of these transformations can be put into a single function. You don't always get every single transformation in every single function, but that can happen. So it's worth talking about what that looks like. Okay, here's an example of a function that involves a cosine, but it has every transformation that we've talked about in it. This looks a little different because I was putting it at the end, plus 1. But oftentimes you'll see a 1 plus instead because it gets it off the back of the function and it helps alleviate any confusion about where that 1 plus is. It's not part of the argument for cosine. It's not part of what's inside the parentheses here. It's completely separate. And if we put it first, that's very, very clear. So this function has a vertical shift. We're going to graph some cosine function and then shift it up 1 unit. It's got a horizontal shift, and how much of a horizontal shift is not quite clear yet, and I'll go over that in just a minute. It also has a vertical stretch. Once I've settled on my cosine graph, I'm going to need to double all my y values. And it has a period of something other than 2 pi. It's actually 2 pi over 3 because this is my k value. All right, the first thing I'm going to do here is rewrite this as 1 plus 2 times the cosine of, and I'm going to factor that 3 out, because now when I factor out a 3, I'm really dividing by 3, so that's going to give me pi over 6. And the reason I've done that is because this is actually the graph of the cosine function doubled but then shifted to the right pi over 6 units. If I shifted pi over 2 units, that's not what this graph is. It shifted pi over 6 units. So to find that value, you need to factor this 3 out first. Notice that that doesn't change how many cycles of the graph I'm going to get. I'm going to get 3 cycles of the graph. So my period here will be 2 pi divided by 3. And what that means is that it's going to take me between 0 and 2 pi over 3 to get 1 full cycle. Now I've been graphing cosine graphs by starting with, by graphing the points for x equals 0 and 2 pi, and then pi, and then the zeros in between. But I can't just do that this time because my period isn't a full 2 pi. So it might actually be quite beneficial to label a few more x values here. In fact, we're going to label quite a few more. That's pi over 2, this is 2 pi over 2, so this is 3 pi over 2, and I still don't have a 2 pi over 3 showing anywhere here, so I still don't know where to end. It's going to be somewhere short of pi because this is only 2/3 of a pi, right? But where exactly? Well, let's see, if I divide one more time, and this is pi over 4, and either side of that I'm going to have pi over 6 and pi over 3. And then halfway between pi over 2 and pi, here's how I tend to do these. I go pi over 2 plus pi, and then I take the average of those two. Well, that's 2 pi plus pi is 3 pi divided by 2, all divided by 2, so that's 3 pi over 4. So this is 3 pi over 4, and then I'll have reference angles there as well. Now, with this one, I could have said pi minus pi over 4. That's 4 pi over 4 minus 1 pi over 4. So that's 3 pi over 4. I can do the same thing with these ones. This is pi over 6 less than pi, and this is pi over 3 less than pi. So if I think of this as 6 pi over 6, and I subtract 1 pi over 6, that gives me 5 pi over 6. And if I think of this as 3 pi over 3, and I subtract 1 pi over 3, that gives me 2 pi over 3. And now I can see where my graph is going to stop, right? Because I know it goes from 0 to 2 pi over 3, because that's what my period is. So I have to take a graph of cosine somehow and squeeze it in here. That's actually going to go like this. The other way to think of this is that that is a third, because I get 3 cycles out of this graph. It's a third of 2 pi. So I'm going to get 1, 2, 3 cycles between 0 and 2 pi. Only one of those cycles goes a third of the way, 1/3 of 2 pi. Now for a normal cosine graph, I'd put a point here, no, I'd put a point here actually, right, 0, 1, and 2 pi 1. I put points there, and then I go to pi, and I come down to -1, and then halfway between I graph my zeros. I can't do that here though, because my graph has to end at 2 pi over 3. So I'm going to plot a point at 0, and I'm not there though, sorry. I'm going to plot a point at 0, and then I'm going to plot a point at the end of my 1 cycle, which is at 2 pi over 3. That also has a height of 1. So I'm going to have a point here. Halfway between 2 pi, between 0 and 2 pi over 3 is the average of those, which is 2 pi over 6, which is pi over 3. So the other extreme value, the -1, goes in at pi over 3. X equals pi over 3, y equals -1. Now, I also need zeros halfway between my x value of 0 and my x value of pi over 3. Half of pi over 3 is pi over 6, so my 0 is going to go there. And on the other side, I need to go, what's halfway between pi over 3 and 2 pi over 3? Well, let's find out. Pi over 3 plus 2 pi over 3. The average of those is going to be 3 pi over 3, which is pi over 2. So I have another 0 at pi over 2. So I'm going to go ahead and connect the dots here, but it's important to note that my work is far from over. All I've really managed to do so far is to graph y equals the cosine of 3x. That's all I've done. What I have to do now is shift it to the right 6 by pi over 6, double all of my y values, and then add 1 to all of my y values. So I've done this in a thin white line. I think I'll do the next one in another thin, maybe I'll do a thin yellow line for the horizontal shift. And then we've already dealt with the 3 because that just tells us about the period, or it tells us how many cycles. If I go all the way between 0 and 2 pi, I have 3 of these cosines. I have 3 cycles. So I've dealt with the 3, but I need to deal with the pi over 6, and then the 2, and then the 1. All right, so the next thing I'm going to do is take all of these points, all these white points, and move them to the right, pi over 6. And I've got them there now in yellow, and so I'll take the same curve and trace over the yellow points, making sure my curve is nice and smooth. So what I have now is y equals the cosine of the quantity 3x minus 2 pi over 2, or the cosine of 3 times x minus pi over 6. These are equivalent. I just factored that 3 out. All right, so this is my, let's see, I did the 3 by finding the period in white. I dealt with that pi over 6 in yellow. Now I'm going to deal with the 2. And just by way of reminding you, y equals the cosine of x and y equals 2 times the cosine of x are related in that the graph of the 2 cosine of x is just twice as tall as the cosine of x. This right here, get the right color pen, this is just my cosine of x. And if y is equal to the cosine of x, then this y is equal to twice as much as the cosine of x. That's really all that's saying. So really, to deal with that 2, all I need to do is take all my yellow dots and double their y values. Double 2 and I get, double 1 and I get 2. Double 0 and I still get 0. Double negative 1, I get negative 2. Double 0, and then double 1. Notice that I'm doing that over the yellow graph because that's kind of the stage that I'm at this point. And back up the other side. Okay, the last thing to do is to add 1 to every y value in my current graph. So I'm going to take that green dot that's at a height of 2 and move it to a height of 3. The green dot that's at a height of 0 gets moved to a height of 1. Everything gets moved up 1 unit from where it was on the green graph. So my current, and actually my final graph, is this thick blue line. These tend not to be too difficult unless you're dealing with this 3 here. I mean, you can look at this and say, oh yeah, there's 3 cycles between 0 and 2 pi. But where people get stuck is realizing that it's not 3 times 2 pi, it's quite the opposite. It's 2 pi divided by 3. And the other really tricky thing is knowing to factor that 3 out. Okay, the horizontal shift here is pi over 6, not pi over 2. There's actually still quite a bit more we could do in this video. Specifically, one of the skills you'll be asked to use is that if I give you a graph, I'd like you to come up with an equation for that graph or a function that represents that graph. I'm not going to do that on this video, and in fact, at the time that I'm making this recording, I'm not going to take the time to make that video at all. If I have time, I'll come back and make it later on. For now, though, basically all you have to do to answer that question is work in reverse. Figure out how wide your graph is. How long does it take to make one cycle? That's the period. Then use the formula period equals 2 pi over k to figure out what this number is here. When we did these, we knew k, it's 3, so we just divided 2 pi by k. If I knew the period was 2 pi over 3, I'd stick that here, and that would tell me what k was. So I just need to think in reverse. Then look at horizontal and vertical shifts and horizontal stretches. You should be able to use the basic form of any trigonometric function, y equals a plus or minus, and I'm just going to leave it as a plus because the next number could be either positive or negative, b times either the sine or the cosine of c times x minus d. Now, it's not always in this form. Sometimes it comes to you in this form and you have to put it into this form. But once you know what the shape of your graph is, looking at 0, is it closer to a sine or a cosine? Does it start at the x-axis and go up, or does it start above the x-axis and come down? Once you know what the basic shape of your graph is and you have the equation in this form, you have the equation of the function. So again, I'll try to make a video for this particular skill later on and add it to the Canvas page. But for now, if you see a graph and you're asked for the equation of that graph, think about this sort of template, that you want your equation in this form, and then think about all the transformations that we've done and just think about them backwards. Specifically and carefully think about the period so that you don't get that part wrong. Remember that this number c here is not the period, that's your k. Your period is 2 pi divided by k. Okay, as always, there's more to come. In the next video, we're going to be looking at how to use calculators and other graphing devices to explore the sine and cosine functions.